Hi, my name's Andrew McLaren, and I'm going to be explaining Lewis structures, octet rules, and resonance, and how to do these in a slightly different way than you've probably seen in your class. But if you follow along with me, I promise you will have a much stronger understanding of these and be able to do them consistently. We're going to be doing a number of problems that I've selected to kind of highlight some things in order. We're going to start with some basic ones. We're going to clarify what's going on with this octet rule, which is kind of more like an octet suggestion to me, and then go over resonance, major, minor contributors, like what's really going on with this in terms of reality and why we see a lot of this in polyatomic structures, as well as common ways to draw this. So this video will be fairly long. It'll cover quite a few topics, but if you stick with me, it will be worth it. When I start teaching Lewis structures, I ask students if they think these things are real and why. It's a really important place to start because Lewis structures, while they're close to reality, they aren't actually real things. So the answer to this is no. Lewis structures not real. But the question then would be why? It's because electrons are not stuck in place. So we do orbitals to figure out where they should be roughly at any given time. Like they're more likely to be in a certain area and less likely to be in other areas. So it really helps to think of electrons as more of like in a cloud or a density. And that is a more accurate way to look at these chemicals. If we're talking about formal charge, this is really just a local charge for like a particular element in a molecule. If it's got a negative formal charge, that means there's quite a bit of electrons around that, usually. So we create a map of this using colors oftentimes to show things like water. You may be familiar with its Lewis dot structure where you've got some dots near the oxygen showing those electrons there, but it is more accurate to show it as a color difference. So this might be a negative area and a positive area for the molecule, and some kind of neutrally charged areas in between where it's not super negative, not super positive, but somewhere in between. And if we look at the same thing for a molecule like carbon dioxide or CO2, you can see that it has a positive and negative charge locally. You can show this with a number of things. I'll show these Greek, I think, letters to show partial charge, like partial negative, partial positive, around the negative being the oxygen and the positive being the carbon. So these big picture ideas are going to be critical for understanding how to actually draw these out. We'll go over my method for keeping track of this. It's not so much like a list of steps, but three main factors that we will go over in detail with plenty of examples. We're going to start with the two examples that we've just looked at with hydrogen and oxygen and water. Now, if you look at this molecule, you'll oftentimes pick a central atom, and oxygen is a better pick here than hydrogen because it's going to have a slightly different charge than the things around it. So oftentimes things will kind of take charge or give charge in coordination with like the things around it. So there might be like a positive core or a negative core. And in addition to that, oxygen does follow the octet rule more closely than hydrogen, which it's more of like, it just doesn't really quite make sense. And we will go over why the octet rule doesn't make sense for hydrogen when we get to the next part. But for now, we're just going to start with something that's familiar. So if we have water right here, what I like to do for just drawing out Lewis structures is think about the total electrons and counting them out. I also like to think about the formal charge of each individual atom, and that should have more negative charges on the electronegative things. On the electronegative. So things like fluorine are going to be very electronegative. It's like the most electronegative thing. So if you're going to be putting a negative charge on an element in a compound, you want to have it be something that's like from that upper right corner of the periodic table, due to it wanting that negative charge more than the other atoms around it. And then we also want to think about the octet rule, which is going to be a bit more complicated than just always putting 8 electrons on things. But generally, we have 8 electrons around an atom. There are some exceptions to this. If you're in the third shell, you can have more, but it does not have to. So this prefers 8 electrons if possible. And if it's in the very first layer, like hydrogen or helium, these guys are going to be having 2 electrons in their outermost shell. So generally we want to have 8 electrons in our outermost shell unless we have more orbitals available. And then if we have hydrogen, it's just limited to 2. So if we're looking at water here, its total number of electrons right now that I've got drawn out here is not quite correct. So I need to get the total number of electrons to be appropriate. So you can do that by keeping track of how many electrons these are each contributing, and then multiplying appropriately and adding them up. So I've got 1 oxygen, and I've got 2 hydrogens. So I've got 2 electrons coming from this and 6 electrons coming from there, meaning that I should have a total of 8 electrons. Currently, I've only drawn in like 1, 2, because there's 2 electrons in each bond. So there's 1, 2, 3, 4, and I need to have 5, 6, 7, 8. Now these are going to be located in this region. We oftentimes depict that with these orbitals to show roughly their geometry or bond angles that they should be forming. This is going to just be a way of tracking roughly where the electrons should be and telling you the shape of the molecule. In addition to that, we can look at the formal charge. And to look at the formal charge, you split the electrons in bonds and you say, how many electrons does this normally have versus how many does it have now? So if I look at hydrogen here, it's got access to just 1. It normally contributes 1 electron, or it's got 1 proton, so an electron balances that out. So its formal charge would be 0. For both of these guys, it's not plus or minus, its formal charge is 0. For the oxygen here, I'm seeing 1, 2, 3, 4, 5, 6 electrons that it has access to if we're splitting it 50-50 between these 2 bonds. So if we look at its formal charge here, it would have a formal charge of 0 because oxygen has 6 protons in it. So if it has access to 6 electrons, its formal charge is 0. These are not the actual charges because the electrons aren't split 50-50, but we're trying to have there be a formal charge of 0 if possible. If we can get that to be the case, that means that electrons are roughly canceling out the number of protons in that region of the molecule. And we want to spread electrons out, and opposites attract, protons and electrons attract. So there is some reason to this rule, but if there's going to be something that wants electrons more, you're going to put the negative charge in that part of the molecule. So water right now, it looks like how we've drawn it is good on the total number of electrons. If we look at the formal charge, it is also looking good. So I'm happy with its formal charge. I'm happy with the total number of electrons. And if we also look at the octet rule here, this is fantastic. So I'll do smiley, frowny, or even neutral faces. And the tricky thing with Lewis structures is that sometimes you can't make all of these perfectly happy. So you have to think about how they compare or combine in the best way possible to get something that is actually accurate. Next, let's look at carbon dioxide. For its total number of electrons, carbon is contributing 4 electrons, and then oxygen will be contributing 6 electrons each. We have 2 of those, aka 12 electrons from here, 4 electrons from here, for a total of 16 electrons. And I do suggest you write electrons here for when you do charged particles later. It will come in useful for just keeping track of Are you talking about the negative charge here, or like the positive charge in terms of what you're adding up? Weirdly, it can get a little bit backwards when you're in the middle of these problems. So I just recommend doing that way. So we've got our carbon dioxide. I'm looking at that. I'm thinking maybe those oxygens will both be a bit more negative than that carbon. So maybe they'll be kind of wrapping around it. And I've done this enough times to recognize that this is a little bit incorrect with how I've drawn it. Carbon dioxide is not going to be like water. It's going to form a straight line. I have some familiarity with this. I know it's also a nonpolar molecule. But if I tried to draw this out like so, and I'm like, okay, carbon has the number of things that I've drawn out here, the total number of electrons is not correct. But if I do something like that, then the total number of electrons would be correct. So this drawing as is good for the total number of electrons. But if we look at the formal charge on these guys, we're going to be getting like a +2 right here. And that means this is I think a -1 and a -1, because this has access to 7. It normally contributes 6. So it's kind of got more electrons than it wants, if you will. So this isn't ideal because we have a bunch of negative charges and we have some positive charge, so we might be able to move electrons around to do better than this. So the formal charge here it's okay because we have negative charge on things that are more electronegative, but it's not the best. And if we look at the electron density here, the octet rule is not being followed for carbon. So it's got like some empty orbitals in here, which is not ideal. It's got quite a few protons in that carbon atom that just does not have access to electrons. So it's like a really positive part of the molecule with what we've drawn as is. So what I would suggest you do is drawing these out and trying to tweak your drawings. I really suggest just keeping your old thing there and working down below. So if we wanted to draw this out again and try and do better, there's some slight tweaks that we could do to this. So we'll have carbon in the center. Let's try these 2 oxygens off to the side. And what I would suggest doing is moving some of these electrons where it's negative to helping it be where it's a little bit more positive. Now we could try and just put some lone pairs on here like so, but then you're going to run into similar issues as to last time. Now we do have, what's that, 6, 10, 16. We do have the correct number of total electrons here, so yay for that. But for the formal charge, now carbon's got access to 6 electrons. It's only contributing 4, so this is not good. We've got really, really bad charge distribution given these things tendency to want electrons or electronegativity. So this is just absolutely terrible for that. But it is actually better for the octet for the carbon. Unfortunately, it's not very good for the octet rule for the oxygen because there's these open orbitals now that just don't have any electrons in them. So it's okay because of the carbon, but maybe like a little bit bad because of that oxygen around it. Which can be not such a big deal if you're talking about these things around the center. But that central atom you want to be really careful with and its orbitals. So if we think about tweaking this slightly more, you probably already know what to do based off of our other ideas. It's like, well, we moved too much charge to the carbon. What if we try and have these things share some more? What if we have a double bond there and there? And if we do that, then we actually have the correct number of total electrons because we've got 4, another 4, so that's 8, another 4, 12, another 4, 16. So it's good on the total number of electrons. And I think the formal charge is actually pretty good too, because if you think about this, carbon has access to 4 electrons, which it normally does, so its formal charge is 0. And carbon, it's got access to 6 electrons, canceling out 6 protons, meaning their formal charges are also 0 here, here, and here, meaning that this is pretty good. we've canceled out that local charge of the protons with those electrons. And in addition to all of that, the octet rule does look like it's being followed. So the oxygen here, this oxygen, has access to 1, 2, 3, 4 orbitals, which contain 8 electrons. So that is fantastic. And in addition to that, we've got like the carbon. It has access to 1, 2, 3, 4 orbitals, which contain 8 electrons. So that's fantastic for its octet rule as well. So it's kind of weird, but this octet rule is saying like how many do they have access to? And if you put something in a shared bond like that, both atoms involved in that bond have access to that for the octet rule. I think of it more as like a 4 orbital rule for most atoms, because 4 orbitals contain 8 electrons. So our drawing is pretty good when we do the carbon with the double bonds with oxygen. This process is a bit different than what you may have learned in your class, but it is extremely useful for the harder problems. So we're starting here simple, we're building up. So if we're looking at the next molecule here, C2H2, I'm going to do this actually correct the first time just to streamline it. But you can see that it is going to have 2 hydrogens and 2 carbons. Now you could try and put some lone pairs around, but the carbons are each going to be contributing 4 electrons. We have 2 of those. And the hydrogens are each going to be contributing 1 electron. And there's 2 of those. So if we think about this, we've got 8 electrons plus 2 electrons adds up to a total of 10 electrons. Currently, I've got 1, 2, 3, 4, 5, 6. Now I could try and do something kind of like this, but it does not satisfy our octet rule. In other words, that carbon has more room for electrons around it. If you've got larger atoms, they can fit more electrons around them or more orbitals around them. So this is going to be a place where you might want to do like a double bond or something kind of like that. But hydrogen, it only has access to 1 orbital as it's in that first energy level. So you only get 2 electrons in there. And then we would be forced to do something kind of like this. Now carbon does have access to 1, 2, 3, 4 orbitals and 8 electrons now. So it's following its octet rule with the current drawing. So what we have drawn, it looks to me like we've got 1, 2, 3, 4, 5 bonds, which would be 10 electrons. So we're good for the total number of electrons, which we kind of kept track over here. A little color coordination always helps. And then if we're splitting these bonds evenly and looking at how much electrons they have access to, hydrogen is going to be having a formal charge of 0 there. Carbon also has a formal charge of 0 here and here. Seeing how the carbon has access to 1, 2, 3, 4 electrons in terms of just splitting those evenly for formal charge. For the octet rule, this is also looking pretty good because carbon has to follow that octet rule or suggestion. It only has 4 orbitals that it can work with, so it strictly has to follow that. And hydrogen only has access to 1. So it's looking good in terms of that rule set as well. NH4 plus or ammonium is a great example because now we've got charge on here. So nitrogen, it's going to be contributing, I believe, 5 electrons. Hydrogen is going to be contributing 1 electron overall, but we have a +1 charge, so it's like -1 electron from that overall charge. Now we do have 4 of these hydrogens, so they're contributing 4 electrons, 5 electrons, and we're subtracting 1 of these electrons here as well to account for that overall charge, meaning that we should have a total of 8 electrons. So this part right here can be a little bit tricky. That's why I put the electrons with those numbers. So we're remembering what we're doing. We're not adding up charge, we're adding up electrons. So you got to flip your brain just a little bit for that. But we've got our NH4 plus, and if we want to draw that, you may be somewhat familiar with what this looks like. If you've done any organic chemistry or biology, amine groups typically have like an R chain off of here. So it's very similar to something like that. And we can see that in this case, we do have 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons in our drawing. So we're good off that. Our formal charge is also looking pretty good because each hydrogen has access to 1 electron, which it normally does. And in this case, the nitrogen is got access to 4. It normally has access to 5. So this is going to be a +1 formal charge. It isn't ideal because nitrogen technically is more electronegative than hydrogen, but this is the best that we can do. So the formal charges here I'm like not that thrilled about, but the octet rule is great. So if I tried to draw something else where I was bringing electrons down to that nitrogen, I couldn't bond to the hydrogens. So one thing that I like to contrast while we're doing the NH4 is if we do NH3, it looks very similar, but you're going to have a lone pair on the nitrogen. And you can go ahead and think of that as a challenge problem. Go ahead and count through the total number of electrons, check out the formal charges there, and even the octet rule. It looks like it has 4 orbitals that has access to, and in this case, 5 electrons. So its formal charges are pretty good for the NH3. If we look at pH3, the phosphate here, it is actually in a different part of the periodic table. It's actually in this 3rd energy level. So while it can break octet, it also can still follow that. There's some stability from having the geometry of just having the 4 orbitals. So this is still going to follow that rule. We'll go over that a bit more soon. But for the purpose of this part of the video, we're going to just look at the total number of electrons as 5 electrons being contributed by that, and each hydrogen is contributing 1 electron. If you have a hard time with remembering that, the periodic table, these have like 1, 2, 3, 4, 5 electrons in that outermost shell. So that nitrogen has, and that phosphate, they are very similar in their outermost shell with having 5 electrons. And we can keep track of the 3 there. So we've got a total of 8 electrons that we should be trying to draw out. And if you are cluing into the last thing that we drew with the NH3, this looks very, very similar. You're going to have a lone pair with the phosphate there. And by doing so, we've got 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons, or 1 octet around the phosphate. So our total number of electrons is good. If we look at the formal charge on these, this has access to 5 electrons, which it normally does. This has access to 1, which it normally does. Good on those formal charges. There's not like a very negative or positive part of this molecule. They're pretty evenly spread out. There is a bit more of a negative charge here because it is more electronegative in terms of reality, but in terms of formal charge, we balanced it out. It's close to even in reality as well. So if we look at the octet, yay, it's actually being followed, and it can be followed by these things lower down, but they can also break that rule due to having more octets available to them. I'll go over that soon. While this is the basic part of the video, this is one that I found a lot of students struggle with drawing out. Now, if we look at the oxygen, its rules are going to tell us that it has 6 electrons that it's contributing, and fluorine will be contributing 7 electrons by their location in that periodic table. Oxygen being 6, fluorine being 7, number of electrons in that outermost shell. And we also have a negative charge, which means we've got 1 more electron. So we've got a total of, I believe, 14 electrons So if we draw out a molecule with oxygen and fluorine, I'm assuming at least one bond between them. Let's try doing something kind of like this. Now that's 8 of our electrons, but another 6. What if we do something kind of like so? This looks pretty good in a number of ways, not so good in some other ways. So the total number of electrons, I'm happy with that drawing. The formal charge though, let's see, that normally has access to 7, and it has access to 7, so its formal charge is 0. And oxygen normally has access to 6, but now it actually has access to 7, so it's -1. But you might see that as a problem. While oxygen is very electronegative, fluorine is more. So why is there a -1 charge on the oxygen? Well, the octet rule is going to mean that this is pretty good. They have access to 1, 2, 3, 4 orbitals each. So both the oxygen and the fluorine are following octet rule. But there might be a slightly different way of drawing this out. What if we try a double bond? What if we bring some of these in down to there? And we consider this molecule now to look something like so. How does that compare? Is that better or worse? Well, it's better in some ways and worse in other ways. So in reality, neither one of these is correct. The electron density is somewhere between these two. This bond is somewhere between a double and a single bond in strength, but one is technically more correct in terms of the rule sets that we do with these. Here, we're seeing a formal charge that looks pretty good. I'm happy with that because we're going to have a formal charge of 0 on the oxygen and -1 on the fluorine. So that's pretty good. Now the fluorine can actually break octet because it is in, or actually no, it cannot break octet because it's right here. So this right now is limited to 8 electrons in its outermost shell. So we got a problem. A big problem. That has too many orbitals, and the second energy level just does not have that many. It only has 4 orbitals, it does not have 5. So the fact that fluorine right now has 1, 2, 3, 4, 5 is a problem. That's a really big problem. So this is not actually going to be closer to reality. The one that is more correct here would be this guy. If we look at oxygen and chlorine, if we have this hypochlorite ion, this is very similar to the last problem that we did, but now chlorine actually can have access to more than 4 orbitals. Because chlorine is in this 3rd energy level, it has access to more. So the better drawing here for the chlorine and oxygen is going to have something that looks a bit more like that. Now I'm going to challenge you to try and go through the total number of electrons, formal charge, and octet rule, and try doing that with the single bond as well. You should see that this one is better in terms of the formal charge, and the octet rule is okay. It's being broken, but with chlorine, because it's a bigger atom, it can have more orbitals around it, so that is acceptable to break the octet rule. And this does have the correct number of total electrons as well. Cutting corners on that one. If you're confused, go back and watch the fluorine video, or part of the video. So to clarify the octet rule, aka that you should have 8 electrons in the outermost shell, that's when you have 4 orbitals, which is if you're in like the 2nd energy level, this is really your only option. So if you're talking about like carbon, nitrogen, oxygen, these atoms that are in this 2nd energy level, they really do have to be strictly following this octet rule. If you go down to the 3rd energy level, let's go ahead and get some diagrams to help you see this. So if you've got the 2nd energy level, you've only got 4 orbitals, 1s and 3p. But if you're talking about the third energy level, they actually have 3d orbitals. Even if those are unoccupied, if those are empty, you can still use them to hybridize or create bonds. They're still there. There's still extra room wrapping around that central atom, if you will. So if you're talking about atoms that are kind of right here in the periodic table, their d orbitals are oftentimes not actually filled in. So if we're talking about like silicone right here, silicone can break octet because it has access to these 3d orbitals. It doesn't always do so. It can still follow octet. There's stability in doing so. If you've got nice geometry canceling things out, and if you look at S and P orbitals, you'll see that how they actually cancel out geometrically a bit. So that's good. You don't want to have like a negative side to an atom or a positive side to an atom if they can cancel out. And that's the big picture on the octet rule, is that it's all about what energy level you are and how many orbitals you have access to. And if you can use them, you should. If they're accessible, you should. With like the octet rule. Like if you've got BF3, it's like, that one probably, you'll see when we look at an example why it's like, oh yeah, that's a little bit weird. If we're looking at BF3 or boron trifluoride, we've got a boron which is contributing, what is that, 6 electrons, I believe? No, it's contributing 3 electrons. Okay. See, that's why we want to check the periodic table when we're a little rusty. I'm doing this during summer. I actually have not tutored for this in a while. But the fluorines are each going to be contributing 7 electrons. And so we've got 21 electrons coming from that, plus the 3 from the boron. So we've got 24 total electrons that we should be drawing out. Knowing what I know about this, I'm pretty sure that this is going to actually have 3 bonds with the boron. If you tried to put like another bond here or another lone pair, what you're going to run into is that you just don't have enough electrons. So this drawing right here, if I drew that in, its total number of electrons is bad. So how do we fix that? Well, we do it without those lone pairs on there, and that's going to be the best fit that we can do. It's not ideal, but sometimes we got to work with less than ideal situations, right? So if we're trying to draw this out in a more accurate way, we can try doing that. And we've got, I believe, 24 electrons. Sometimes I'll do like, okay, that's a group of 8, that's a group of 8, that's a group of 8, just to do a pinwheel of counting out from the center and going around. And it looks like, yeah, 8 times 3 would be 24 electrons. So that's pretty good for the total number of electrons. The formal charge on these guys is actually decent as well. So these guys have formal charges of 0, because boron, it has access normally to 3 electrons. In this arrangement, it's getting about 3 if we split those bonds 50-50. So I'm happy with that, as well as the total number of electrons for this version of the drawing that we've got here. And the octet rule is definitely not being followed here, so I'm not happy. I'm a little bit bummed out about that, but we just can't do better. We definitely need to account for all of the electrons being there. We can't just put on extra ones here. So that's like the best fit with the combination of these rules. It really is like, you gotta weigh these different things and see what you can do and make them the most happy. And that'll get you closest to reality. If we look at the compound PF3, it does look very similar in the writing of the formula to BF3, but be careful. It might be a little bit different due to the total number of electrons that it contributes. If we look at phosphate, it is going to have 5 electrons because in the periodic table, it's right here. but also it's in the third energy level, so it could break Octet. That's totally okay for it to do, because it's got access to not just S and P orbitals, but also those D orbitals. Totally okay for phosphate to have access to more places to put electrons. It's kind of a big atom. So we've got 21 electrons from the fluorine, 5 from the phosphate, for a total of 26 electrons. And so if we're trying to draw out this, I'm going to put P in the center, and the fluorines around it. There are a bunch of electronegative things around this like more positive core. And I'm thinking, let's just start placing these on here. It does kind of seem like it might be like BF3 at first, but if you count these number of electrons that I've got drawn here, I need 2 more. So if I put those right there, that works pretty nicely. Now you might be inclined to make it like a double bond or something like that. You would run into some issues if you were to do it like so. One of the main issues being the formal charges just aren't quite right. Like, yeah, the formal charge on this is 0, formal charge on that is 0, but now this fluorine has access to 1, 2, 3, 4, 5, 6, 7, 8. So it is a -1, and that is a 0. In other words, there's too many electrons near that fluorine. Sorry, this would be not a 0, because the formal charges should add up to the overall charge, which is neutral. So this is actually, yeah, like a +1 on its formal charge, because actually it's got 1, 2, 3, 4 electrons, and normally has access to 5, so it's not quite canceling out. And this means that we should have more electrons near the phosphate. So this is not good in terms of the overall drawing. It's okay in terms of the number of electrons, but the formal charge is pretty problematic. And the octet thing is, it's okay to do what we've got here. We've got 1, 2, 3, 4. That seems to be all right. So I think that is completely acceptable so far. Phosphate, while it can break octet, if it could follow octet, that's also acceptable. It's just got like S and P orbitals kind of geometrically canceling out. And there's no need to use any other orbitals. If there was, it might be able to use those. But as of right now, the best way to draw this would be kind of like what we've talked about. Having the phosphate with 2 lone pairs, or 2 electrons in the lone pair around it. So we've got 3 fluorines, 1, 2, 3, 4, 5, 6 lone pairs around each one. And they're following octet, though they could break that themselves, fluorine being in the 3rd energy level, or 2nd energy level, it actually has to follow it rather strictly. So this works because it's got the correct number of total electrons. If we look at the formal charge on these, it has access to 7 electrons. Normally it has those. It's got 7. They balance out with the number of protons that you've got there normally. And then we've got the phosphate here is 1, 2, 3, 4, 5. So it is also got a formal charge of 0. So we've got a nice amount of electrons considering the number of protons around each part of these atoms. So the formal charge here looks pretty good. And the octet rule is being followed here. Although you could break it, it is not necessary for this molecule. And you could break it because phosphate is in the 3rd energy level. Actually, considering that, I'm going to correct one minor point. This drawing that I did earlier, I'm actually going to say is a bit problematic due to this guy right here. 1, 2, 3, 4, 5, 6, 7, 8. These orbitals, we've got 1, 2, 3, 4, 5 orbitals around fluorine. So this is actually not great. That drawing has some problems, not with the central atom, but with these other atoms around it. So this is a much better model for our molecule in the end. Now, if we're looking at PF5, this is very similar in the atoms involved, but we need to just count out the electrons and draw it out. So the phosphate, like last time, is contributing 5 electrons. Fluorine is contributing 7. But this time, we're getting more electrons from the fluorines than we were last time. So we've got 35 electrons from there, 5 from there. So we've got a total of 40 electrons. It's a lot to count, but you will get better with this with practice. Now, you might try and do something similar to last time. You were to do like a lone pair here, and then you've got 5, 1, 2, 3, 4, 5. But those of you who are kind of more quick will realize that I've got 2 more bonds, and that takes 2 electrons from here. So there isn't actually a lone pair on here. It's most likely fine as is, drawn as is, with 1, 2, 3, 4, 5 bonds with the fluorine. And then the fluorine, they do have a few lone pairs on them as well to fill their octet, because fluorine's in that second energy level. We're going to want to have 4 orbitals or 8 electrons that it's interacting with. If we count this out, what I would recommend doing is doing like 8 times 5, because we've got 1, 2, 3, 4, 5, 6, 7, 8 like spokes on a wheel. And that if we do 5 times 8, we should get 40. So that does look good in terms of the total number of electrons. If I tried to have another lone pair on here, that would be too many electrons. If we look at the formal charge now, this has access to 7. It normally has access to 7, so its formal charge is 0. This has access to 5, normally has access to 5, so its formal charge is 0. So we're pretty good on that as well. Now the octet rule here is being broken for phosphate, but that's okay. So I'm not the most thrilled about this, because phosphate, if we could follow octet rule, that would be great. But because of it being in this 3rd energy level, there's more room for more orbitals. So you can have like those d orbitals being used, and you can put electrons in there to hybridize and form bonds. So this looks pretty good, and this is the best that we can do. You might consider trying to put like a double bond on one of these, but that's going to end up causing the formal charge to be like a positive number on all those fluorines, which we don't need. If we can get the formal charges all to be 0, we can evenly spread out all the electrons in a neutrally charged compound, and that's great. That's what we're trying to do. We're looking at the molecule SiF4. Silicone right here is going to be contributing 4 electrons. And fluorine, as we've talked about a few times, is 7 electrons, but we have 4 of those. 7 times 4 is 28 electrons. We add up the total number of electrons, and we get 32 electrons. So if we are trying to aim for 32 electrons, that can help us draw this out. Now I'm looking at the atoms involved. Silicone is in the 3rd energy level, so it might be able to use more than 4 orbitals, so it can have more than 8 electrons. So it's breaking the octet rule, where it can go a little bit bigger or having more bonds. I'm going to probably put that silicone in the center, and then I think 1, 2, 3, 4 fluorines. And I'm pretty sure if we just count out the electrons that make sense for following octet for fluorine, then that is close but not quite right, because fluorine does have to strictly follow octet. It's got s and p orbitals, so we're going to try and do that. It could potentially have less, but it really is stable if you can get full octet for something at 2nd energy level. So we've got right here, I'm seeing like 8 electrons basically times 4, which is pretty good, right? So we've got 8 times 2, 16, and times that by 4, you get 32 electrons. So SiF4 is something that it could potentially break octet, that silicone, but it actually doesn't. It's totally fine. And if we look at this, we're going to have formal charges that are appropriate as well as having the total number of electrons. That makes sense. The silicone is contributing 4. It has access to 4 electrons. Fluorine has access to 7, which it normally does. So the formal charges look great on this, as well as the total number of electrons. And everything is following the octet rule. Silicone, while it could potentially break the octet rule, it does not need to. It could use S and P orbitals if it gets that geometry from that. So it looks good as is. If we're looking at the compound SF6, this is going to be a bit different because we don't have silicon now, we've got sulfur. Sulfur is going to contribute 6 electrons. It also can break octet. So we have to keep that in mind, like it might be involved in more than 4 orbitals. So we've got fluorine contributing 7, we've got 7 times 6, got 42 electrons, 42 the meaning of life. We add those up and we get 48 electrons. I'm a nerd, I have to do those references still to obscure books and stuff. I'm looking at this, I'm seeing fluorine has, there's 6 of them. They each need 1 electron. Sulfur has 6 electrons. So I bet if we were to just do this with 1, 2, 3, 4, 5, 6, that would be an appropriate amount of electrons total. Now I will have to have the lone pairs on the fluorines. We can add those in, but while we're doing that, you can see how the fluorine is giving 1 electron to the bond and the sulfur is giving 1 electron to the bond. And that means that their formal charges are fantastic. This has access to 6 electrons, so its formal charge is 0. Each one of these fluorines has access to 7 electrons, so their formal charges are also 0. And if we look at this, we've got 8 times 6, which would be 48. So we've got the correct number of electrons. I'm doing that by doing like 8 right there and then timesing that by 6. Just there's a number of ways that you can add up these electrons. That is one trick that I find that a lot of students don't do, but it's just an alternative way of counting them up. Now the octet rule is being broken for sulfur here, but because it has that 3rd energy level, it has access to more orbitals, not just the S and P orbitals, but also some d orbitals being in that 3rd energy level. So it's not really following the octet rule here, but it's following its own version of the octet rule, where it can actually use more if possible. That being said, silicone sometimes will only have 4 orbitals involved or 8 electrons around it, but not in this case. It worked out in this case. If we look at sulfur and having 4 fluorines, though, the SF4, this is going to be where we have, I believe it's going to actually follow the octet. So sulfur has 6 electrons, and fluorine is contributing 7 electrons each. There's 4 of those. We got 28 electrons from the fluorine plus the 6 from the sulfur. We add those up. We get, what is that, 34 electrons. And if we try and draw that out, you can get 1, 2, 3, 4 fluorines around that sulfur. And fluorine really should be following its octet because it's in that second energy level. It does not have d orbitals to work with, so we shouldn't really do a double bond. Like if you tried to do a double bond here and here to justify this, that would be bad for the fluorine's octet. So I'd be upset about that due to this guy having 1, 2, 3, 4, 5. We're not actually going to do that version of this. If we want the sulfur to have 6 electrons, if you just put a lone pair on there, that actually should do the trick. Because if we split the bonds 50-50 for the formal charge, it's got 1, 2, 3, 4, 5, 6. So you can kind of see a pattern here. And it's very similar to the other problems that we were doing earlier with the fluorine and the lone pair being used to maybe make some more bonds if you've got more atoms. But the fluorines here, they have to follow the octet pretty strictly, and they look like they are, as well as having the formal charges be good. So in this case, we have the total number of electrons correct, because we've got 8 times 4, which would be 32, plus another 2, 34. And the formal charges look all right. And the octet rule, while it's being broken, because we've got 1, 2, 3, 4, 5 orbitals around the sulfur, that's okay. It's definitely, using those d orbitals, but that's allowed because sulfur is in that third energy level. It doesn't always do that, like what we saw in the last problem. It did kind of break the octet, but sulfur doesn't always break that. If we look at the compound of sulfur with 2 hydrogens, we've got the sulfur, which is contributing 6 electrons, and the hydrogen, which contributes 1 each, but we have 2 of those. We add those up, we've got 6 plus the 2, we've got 8 electrons. Now, if we want to draw that out, we're going to need to look at maybe the S being in the center with 2 hydrogens, just solely because the hydrogens can't form multiple bonds with multiple things. They're going to have to be wrapped around the central atom. I'm also thinking that we've only got 1, 2, 3, 4 of our electrons, and I'm thinking maybe we do something like that. With that, we now have the sulfur having access to, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's the correct number total, but it looks like the hydrogens are each going to have a formal charge 0, and this guy's going to have a formal charge of 0 as well, because it's got access to 1, 2, 3, 4, 5, 6. So that looks pretty good in terms of the overall formal charge and the total number of electrons, and also the octet rule, because the sulfur is it's got 4 orbitals. In this case, it will follow the octet. So things that are in the third energy level, like sulfur, they're going to be able to just use the 3s and 3p to get some geometric stability from the electrons being just evenly spread out. So you don't have to use 3D all the time, even when you're in the third energy level, like in this problem here. So it's an option to break octet if you've got that third energy level, but it also can be fine just following the octet with those guys due to that geometric canceling out. To me, resonance is a way for us to have correct for Lewis dot structures and their issues. Because Lewis dot structures are putting electrons in certain locations and not doing electron density maps, they can give the impression of like an uneven distribution where there actually is an even distribution. So if we look at CO3 2-, there's a number of ways that you'll see this represented, but the best way to show this is electron density, because you'll see the carbon in the center is a bit positive, and each one of these oxygens is a bit negative, but they're equally so. There's this symmetry to it. And it's kind of hard to show that in a Lewis dot structure. If you try and draw out an individual Lewis dot structure for this thing, you might end up with something like this, or you might end up with the double bond on one of the other oxygens. These are 3 different versions of the same drawing, but none of them is correct. This bond is somewhere between a single bond and a double bond in terms of strength. So you'll sometimes see it represented as like a single line and a dotted line to show it's like somewhere between a single and a double bond. But then like how many total electrons do you have there? There's no real good way of drawing a Lewis dot structure when you run into these situations where it's like, why put the electrons on this oxygen versus that one? There's no real reason. They're equally valid options. And it's just kind of a messy duct tape fix to the way our system is just putting these things in certain locations. So if you're going through the rules of drawing out a Lewis dot structure, you would look at this and say, okay, I've got carbon, which is contributing 4 electrons. I've got oxygen, which is contributing 6 electrons. And there's 3 of those. For 18 electrons from that, we add those up, we've got 22 electrons. So I should write this out as CO3 2 minus. We do have actually a -2 charge on here. So there's 2 more electrons that are being added to this. So we actually have 24 electrons, not 22 electrons. See, that's why it's important to take the time to actually write this out and think about the charge and how it adds up to those total number of electrons. Then you would take your carbon, you got your 3 oxygens around that, and you start placing electrons on there. If you did something kind of like this, a lot of teachers are going to tell you that you are incorrect. That is not actually true. This is just a minor contributor. It's not as good as the other drawings. So this drawing is like, it's got issues with it, mainly being the octet isn't being followed for the carbon. But here the oxygens are each getting -1 charge, and the carbon's actually getting a +1 charge. If you do not consider this being a minor contributor to the overall thing, then it doesn't make sense thinking of this carbon as a positive charge in that electron density map. It's only going to have that like kind of blue center if you're considering this option. The other drawings that we were looking at just a second ago, the carbon does not have a positive, it's just like neutrally charged. So you do have to contribute like these minor forms, which are not as good, but they do help explain the overall thing when you put them all together in your mind. So the formal charge here is like less than ideal, but it's okay. And the total number of electrons I think is good because we've got, what is that, 8 times 3, so that's 24. And the octet rule is also not being followed here. So this is not a great drawing of the thing, but it's also not correct to say that it's incorrect because it still does affect the overall charge and having like there being some partial charge to the center here. If you were to do the carbon with a double bond on one of these oxygens, it is a bit better. In terms of our rule sets, but it doesn't necessarily give the complete picture because we can look at this and say, okay, well, the formal charges on this sure is going to be a -1 and a -1. This one is going to have access to 6 electrons. It normally has access to 6, so its formal charge is 0, and this guy's formal charge is 0. So if we were to look at that or put the double bond on any of the other oxygens, the carbon would be considered neutrally charged. So if you only consider what we call major contributors or the correct answers, you don't get the full picture because you don't see the positive charge or partial positive charge on the carbon. Now, oftentimes you'll see teachers say only draw these major contributors or like the best drawings. and they would want you to draw all of the equally valid options or resonance structures. Resonance structures aren't really real. They're just kind of a way for us to show something that's close to real when we look at all three of them together. So like this is equally valid if we've got the double bond on this guy, or the double bond on that lower right hand corner. Like all of that is really the same thing that we're talking about here. All right, it's a little bit laggy because I've got the software keeping track of me on camera using the green screen background removal tech, so it's just a little slower. So it's like, why would I have the double bond on that lower right oxygen, or that left one, or that upper right one? They're all equally valid, and these three drawings are usually what you would give as the correct answer for the resonance structure on a test. This is a good compound to look at after looking at the carbonate ion, or the CO3 2-. It's very similar. It's a carboxyl group. So we can add up the total number of electrons and just kind of do it that way. Though if you're used to kind of seeing these things, you might be able to do a little shortcut. So the carbons, they each are contributing 4 electrons. So there's 8 electrons from there. Hydrogen, there's 1 each for electrons, but there's 3 of those. So 3 electrons from there. The oxygen is 6 electrons, but we have 2 of those. So 12 electrons from there. And we have a -1 charge, so that's 1 more electron that we're adding in to our number here. So I believe we've got, what is that, 12 plus 12, or 24 electrons for our total number of electrons. This compound is going to probably have hydrogens that are bound to a single atom because they can't bind to multiple things. They're not going to connect to like anything else like that. So instead of drawing that out, we're going to have a bond to maybe say another carbon, and maybe an oxygen here and an oxygen there. Now you can do a ton of different iterations of trying to draw this out, but this will allow us to have a resonance structure if we do something like so. Because why would you have the -1 charge here versus on the other oxygen? Like it just doesn't really make sense to have the negative charge on one of them versus the other. So there's 2 equally valid options now where we can have this molecule be essentially the same thing, but having a single bond and a double bond for the other oxygen. And these 2 drawings, like neither one is correct. In reality, this molecule has some symmetry going right down this line. And these 2 oxygens, like neither one of them is more negative than the other one. The best way to show that is using resonance structures with like showing the multiple versions. And I'm gonna also add in our hydrogens just to be consistent in that regard. You could also show this with something that looks something like that. But then how many lone pairs do you put around each one of those oxygens? So this drawing is one way to show the symmetry, but it kind of messes up the total number of electrons. So I don't really like drawing it that way, although that is closer to reality in terms of the geometry. If we look at this drawing here, or this drawing here, I believe that has 24 electrons. You can see you've got 1, 2, 3, 4, 5, 6, 7 bonds, or 14 electrons there. And then, yeah, we've got another 5 sets of lone pairs. That's 10 more electrons, so that adds up to 24. Tons of different ways you can add these up, but it does look like we have 24 electrons in those drawings, so that's good. If you look at the formal charge on all of the atoms here, we've got zeros for most of them because the carbon has access to 4 electrons. It normally has 4 electrons, so that's great. In its outermost shell. Same with this one, it's got access to 4. And this has access to 6 electrons, which it normally does, so it's 0. Now this one has access to 7, so it's a -1 for its formal charge on that. If you look at all the formal charges added up together, they should add up to the overall charge because you're just accounting for overall sum of these individual little charges. So the formal charge here looks pretty good in either one of these drawings. And the octet rule looks like it's followed for the carbon and for the oxygen. Hydrogen, it only has 1 orbital accessible to it, so it doesn't really follow that octet rule. It's just like a single orbital for it. So that looks pretty good to me. If we're looking at C6H6, this is a kind of special chemical. We'll go into detail as to why, but the carbon, each they're contributing 4 electrons. We have 6 of those. So that should be 24 electrons from there. The hydrogen is each 1 electron. And we have 6 of those. So we've got 6 electrons coming from there for a total of 30 electrons. If you try and draw this out as just like a single chain, you're going to run into some issues with the number of bonds. What you actually will need to do for this guy is to get them to be in a bit of a ring. This is called a benzene ring. And each one of these carbons will have a hydrogen off of it, as well as access to a double bond. In a sense, that's how we draw it out at least. So you will need something kind of like that. But there's no reason to put that lone pair there versus putting the lone pairs on these 3 spots. So it's really hard to show this resonance structure correctly without thinking about the lone pairs being between those different carbons as well. So it could just be something kind of like that as well, the double bonds and the single bonds. Like there's no real reason for the double bonds to be on a particular spot versus the other spot. But we do have the correct total number of electrons when we have something drawn out like so. You can go ahead and count them up like you normally would and double check that. So our total number of electrons here should be 30. And I'm seeing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 bonds, each having, 2 electrons in it. So that should be a total of 30 when we look at that. So yeah, that looks good as is. If we're looking at the formal charge, okay, come on computer, you can do it. We're almost there. If we're looking at the formal charge on them as well, the carbons each have access to 4 electrons there in their bonds, so they all have formal charges of 0. The hydrogens all have access to 1, so their formal charges are all 0. So the formal charges look great. The total number of electrons also looks great. And the octet rule is being followed because 4 orbitals are involved with each carbon atom. Hydrogen does not have to follow the octet rule. So this is one way of drawing it, where you've got the arrow going between the 2 different equal versions that are, neither one of them is like true or real, but that when you average them together, you get something that is more accurate. So a lot of times people will draw this out kind of like so, with the dotted lines between them to indicate that there's no place that the double bond really is. It's kind of shared between all of them. When you get into more advanced chemistry classes, they'll talk to you about overlapping pi bonds, and so this just has electron densities that coordinate above and below in a fancy way that just works out very nicely. If you ever see a molecule drawn out like So this is essentially a benzene ring. The circle is similar to those dotted lines in there. It's just a way of showing that there's this double bond between a bunch of things. And you'll see a lot of the medicines have benzene rings within them, and like they're attached to a bunch of other carbons. If you're not familiar, you can also represent carbons as like kind of like points on these chains of things, kind of like that. And that's another similarly related structure that you see in a lot of other larger chemicals, like in biology. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. I've got a few other things on here like a Facebook page and our social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.